In this video, we're going to explore the quadratic formula. Now, the quadratic formula is another method that we can use to solve quadratic equations. We've already looked at reversing operations, completing the square, and factoring. Now we have a fourth and final way that we can do this, and it's called the quadratic formula. The nice part is this can work for any quadratic equation that we have. The downfall, though, is it can get pretty messy. So if we have a quadratic equation in the form ax squared plus bx plus c equals 0, so in other words, everything's already on one side, and we have a 0 on the other, we can pick out the a, b, and c values just like we did with the discriminant. We can find the solutions of the quadratic equation using the quadratic formula. And the quadratic formula is x equals, so again we're getting solutions or roots to a quadratic equation, negative b plus or minus the square root of b squared minus 4ac, all of that divided by 2a. Once we plug those numbers in, we're going to simplify. We're going to simplify radicals, we're going to simplify fractions. And that's really all there is to it. But that's the challenging part, is the simplification. You might have noticed that if you're looking at that quadratic formula, that the discriminant is actually hiding in the formula itself. It's right underneath the radical, b squared minus 4ac. In the previous video, we talked about what the discriminant actually was and what it told us about equations. Now this might start to make a little bit more sense now when we say, well, if we had something like the square root of 0, so the discriminant was 0, we're only going to get one root. Because again, if this part's 0, if I add or subtract, it doesn't really change the number. I'm really just going to find this part here, the negative b over 2a. If we said that the discriminant was positive and was a perfect square, then we know that this square root is going to become a whole number. It's going to become an integer. So at that point, we can take a number, add or subtract some other number, and divide it by some other number, and we're going to get a nice looking fraction. If it is greater than 0, but it's not a perfect square, then we're going to have a radical left over. Even if we simplify it, there's still going to be a square root there. That's an irrational number. Actually, two irrational roots because of the plus or minus of it. And then if the discriminant was negative, we can't take the square root of a negative number and get a real number. So we got two complex answers. So as a couple examples here, we have this first one, model 1, x squared plus x plus 7 equals 2x plus 6. Our goal is to get x squared, x, and our constant on the same side. So we're going to subtract 2x and subtract 6 so that we have x squared plus 5x plus 1 equals 0. What that now tells us is that we have it in the correct form. We can now pick out our a, b, and c values. And do one of a few things. One option is we can directly plug that into the quadratic formula. But another option is to go ahead and do the discriminant, because the discriminant is going to tell us whether or not it's factorable or if we got to use the quadratic formula. So let's use the discriminant idea here, the b squared minus 4ac. And when we plug that in, we're going to take 5 squared minus 4 times a is 1 and c is 1. And when we simplify that, that will end up giving us 21. 21 is greater than 0, but it's not a perfect square. So we are going to have irrational roots. It's not factorable. So we're going to apply the quadratic formula. Here's the nice part about using the discriminant when we start the problem. Even if we decide, oh yeah, we should use the quadratic formula, it is part of the quadratic formula. It's a little bit nicer not to have to simplify that when it's underneath the radical. So let's see. We're going to take the opposite of b, so negative 5 plus or minus the square root of the b squared minus 4ac, which we know is 21, and we divide it by 2 times a, which is just 2. So our final answer is this, because we cannot simplify the square root of 21. And so there's our answer. Now, what does that mean? That means that one of our roots is negative 5 plus the square root of 21, all of that divided by 2. And another one is negative 5 minus the square root of 21, all of that divided by 2. So what about a problem like this? 2x squared minus 3x plus 1 equals 5x plus 2. Once again, it's not set up ready to go for quadratic formula or factoring. So I'm going to bring the 5x over to the left side and the 2 over to the left side as well. And pick out a, b, and c values, because nothing's jumping out at me that immediately I know it's factorable. In fact, I have a suspicion that it's not. But if we have this, I can now plug in b squared minus 4ac. So negative 8 squared minus 4 times 2 times negative 1. And that's going to give us 64 plus 8, which is 72. Greater than 0 but not a perfect square, the quadratic formula is the way I'm going to approach this. So my start here is take the opposite of b, so the opposite of negative 8 is 8, plus or minus the square root of b squared minus 4ac, that's the discriminant, 72. All that divided by 2 times a. Now 72, we can actually simplify that, and here's the approach I want to take with this. I want to start thinking about what can go into 72. And one option is to go ahead and start listing out some factors. So 2 and 36, 3 and 24, 4 and 18, 6 and 12, and I think that's about as, 9 and 8 as well. So those are the factor combinations I'm seeing for 72, and I want to look at those factor combinations. When I'm simplifying this radical, I'm looking to pick out the biggest perfect square. So immediately I can eliminate 3 and 24. There are no perfect squares. And same with 6 and 12. So I'm left with these three factor combinations. The one that has a biggest perfect square would be this one. And the square root of 36 is 6. That's going to be a nice whole number. The square root of 2 is just going to remain. So when I simplify that radical, it's going to become 8 plus or minus 6 square root of 2. And the denominator is 4. I'm not done yet, though, because what I'm really looking for are these numbers in front. So I'm just going to highlight those. Any numbers that are in front, I want to look to see if I can reduce all of them at once. Not just like 2, or all of them have to be simplified. But I'm not looking at that number underneath the square root, because I've already simplified that. I've already taken out all the perfect squares. That 2, for all intents and purposes, is buried underneath that radical. It cannot come out. So looking at 8, 6, and 4, I think I can take a 2 out. 4, 3, and 2. And there's our final answer. 4 plus or minus 3 root 2, all divided by 2. All right, one more. We have this problem right here. It's already set up, ready to go for us. It equals 0. So I'm going to take a equals 1, b equals 10, and c equals 5. And again, I'm suspecting it's not going to be factorable. Let's just verify. So b squared minus 4ac would be 10 squared minus 4 times 1 times 5 minus 20 would be 80. Not a perfect square, not factorable. So I'm going to apply the quadratic formula. X equals the opposite of b, so negative 10, plus or minus the square root of my discriminant, which is 80, over 2 times 1. 80 I can break to 2 and 40, 4 and 20, 5 and 16, 8 and 10, and I think that's about as far as we can go. So again, I'm looking for the factor combination that has the biggest perfect square, so no perfect squares here or here. It looks like it's going to be that. 80 will become then the square root of 16 and the square root of 5, which we know better as 4 square root of 5. And at that point, I'm looking at the 2, the 10, and the 4. I can take a 2 out. So that gives me negative 5 plus or minus 2 square root of 5. And you got an option here. Technically, we shouldn't put this over 1, but realistically, yeah, it is divided by 1. So if you had negative 5 plus or minus 2 root 5 all divided by 1, it's technically correct. This is the more accepted convention, though, to how to describe your answer. So again, quadratic formula, it's a nice formula. It does work. It's not something we should use for every single problem. If it's factorable, we should use factoring. It just makes things a little bit easier. But as a last resort, if we have something that isn't factorable, the quadratic formula is a nice way to find our roots.